here's an example of a problem involving projectile motion. I'm just going to run through this, give you guys a sense of what this is going to look like. I've drawn over here sort of a rough vector of this motion. So we're given a baseball that's thrown at an angle of 30 degrees from the ground, and it lands 40 meters away after 2 seconds, right? So this vector here, we'll just label it V, right, is the motion of that ball, right? It's up 30 degrees from the ground, right? And we know that it lands somewhere 40 meters away in the x direction, and this takes it 2 seconds to travel that far. So the question we're asked is, what height does the ball reach, right? This height is something in the y direction, right? So we're given information about the x direction, but we want to know something about the y direction. So the first step here is to sort of see what can we figure out given what we have, right? So we're given the change in position in the x direction is 40 meters, and we're given the change in time, right, to travel that distance, 2 seconds, right? And we know from class that motion in the x direction, right, the x component of this vector follows the constant velocity model, right, CVM. In other words, right, this motion represented here by the, turn that into a vector, right, by the vector component in the x direction, right, that is v sub x, right, this motion follows CVM, right? So we can use the equation that we have from CVM, that is change in position, right, displacement over change in time, is going to equal the velocity in the x direction. So we can figure out what the magnitude of this vector is, right? So that would be 40 meters divided by 2 seconds equals 20 meters per second. Cool. So we have the magnitude of our velocity in the x direction. We have one component, 20 meters per second. Awesome. So how might that help us figure out what height the ball reaches? Well, we have a right triangle here, and we have one side of the triangle as well as the angle of that triangle. So using some right angle geometry, we can determine the magnitude of the component in the y direction. Right, this component, the y, right? Remember, the vector vx and the vector vy are going to be added to each other, right, head to tail, to create this resulting vector. That is the way that the baseball is thrown, right? So we have 30 degrees here, and we have the length of the vector adjacent to that 30 degrees. So we could do, use something like the tangent of 30 degrees, we know equals, right, the opposite side of a triangle over the adjacent. In this case, right, the opposite side of the triangle is Vy, and the adjacent side is Vx, right? So the tangent of 30 times Vx equals velocity y, okay? This is going to be tangent of 30. Make sure your calculator is in degrees, not radians. I made that mistake the other day. Tangent of 30 times 20. That means that Vy is going to equal about 11.5 meters per second. Awesome. So we have a magnitude for Vy. So initially, our ball is traveling 11.5 meters per second in the vertical direction. We know that motion in the y direction follows CAM, C-A-M, right? So we can use big 4 to solve something about the y direction. In specifics, right, this ball, once it leaves the thrower's hand, is in free fall. Right? It's going to have an acceleration of negative 9.8 meters per second squared. Okay, so if the question is what height does the ball reach, we have to do a little thinking here about what's given, right? We're told, go ahead and sketch the path of the ball here, just kind of roughly, right? We're told that the ball, when it's thrown at 30 degrees, travels 40 meters in 2 seconds. We want to know what height it reaches, right? So we want to know what's its position, right about here. The velocity of the ball at this point, right, is going to be 0 meters per second, right? Because it's traveling up with a positive velocity, and then once it reaches its peak height, its maximum height, it's going to fall back to Earth with a negative velocity, right? So velocity here is going to equal 0. The amount of time that it takes for it to travel this height and then return down to a position of 0 height is going to be half of this 2 seconds. Right, assuming that the acceleration is uniform, right? If this is our velocity time graph, right, and this is some positive height, the area of these two triangles have to be equivalent, right, because there's no net displacement, it returns to the same spot. So the initial velocity and the final velocity have to be the same. Therefore, the time interval across these two triangles needs to be the same. So it's going to take it 1 second to reach its maximum height. This is a little tricky, right, the way that this is sort of rationalized, but we'll be talking more about it, right? So we have some new information that we can put into our CAM to find the change in height, right? The change in time from when it leaves the hand of the baseball player to when it reaches its maximum height is 1 second. The V final, when it reaches its maximum height, is going to be 0 meters per second, right? And the V initial, right, is what we calculated above, right? The velocity when it leaves the pitcher's hand, which is 11.5 meters per second squared, or sorry, meters per second. And the acceleration, because we're in free fall, is negative 9.8 meters per second squared. So we're looking for displacement, right, in the y direction. Change in y. Just for clarity, I'll keep it that way. This is the same as change in x, but since it's vertical, I'm going to say that it's change in the y position, right? And we're given V final, V initial, acceleration, and time, right? So there's one of the big 4 that's going to work for this one. Go back in your notes and see if you can select the correct equation for solving this problem. Right? You could do V final squared equals V initial squared times, or plus 2 acceleration, delta x, right? You don't even have to use time there, which is kind of nice, right? You can plug in our numbers here. V final is 0. Whoop. V final is 0 meters per second. That equals the initial 11.5 meters per second squared plus 2 times negative 9.8 squared, right? Make sure you keep the negative in there, times the displacement, right? Our delta y or delta x. So then we go ahead and do some math, break out our calculators. This equals 132.25 minus 19.6, change in y, right? We're going to get negative divide both sides by negative 19.6. And you will get, drum roll please, 6.75 meters equals the change in y. This means that this baseball, right, reached a maximum height of 6.75 meters, right, during this throwing motion. So it seems complicated, right, but if you break it down into each of its components, it's stuff that we've seen before. All right, have a good weekend. I'll see you guys on Monday.